So the big question for you is which optimizer to use when. So we have seen this spectrum of optimizers: mini batch SGD, momentum based approaches, right? And of course, NAG, right? Then we have seen AdaGrad, right, with adaptive gradients. And then we have seen ADA delta, right? We have seen ADA delta and RMS prop type of algorithms. Then we have seen ADAM, right? These are the spectrum of algorithms that we've learned. There are many more algorithms, but these are the most popular ones. Okay, there is a huge literature of tens of algorithms in deep learning, but these are the most popular ones that we discussed, right? The core idea here, okay, let me show you a visualization, a very nice visualization that I'll provide a reference link to in the description section of this video, right? So if you go to this page and if you scroll down a little, this you can find this in a lot of places, right? So imagine that I'm at a saddle point. This is like a saddle point, right? This is like the saddle point. So it compares various algorithms. It looks at SGD with momentum, NAG, AdaGrad, ADA delta, and RMS prop. Except ADAM, all the major algorithms are here in this visualization. You'll notice that your ADA delta is converging fast. So if you just see this, okay, let me start. Okay, see your yellow line moving very fast, which corresponds to ADA delta. Other ones like your momentum based approaches also converge. See, look at your momentum, which is your green line, taking longer time, slowly. Okay, it took a while. Your momentum based techniques took a while to get out of this problem. But if you take your simple mini batch SGD, your red one, it's always stuck there. It's not able to come out. Your simple SGD is not able to come out of this saddle point problem. So one of the big advantages of momentum based techniques is also getting rid of the problem or avoiding the issue of saddle points, of getting stuck at saddle points. Most of the other algorithms, except your mini batch, can get stuck at local optima, or to be very specific, at saddle points, right? So you should always use mini batch SGD only when you have a small neural network, a very small or shallow or very shallow neural network. And if you're noticing that you may be encountering a problem of saddle point, see, when do you know that you have stuck at a saddle point? If with each epoch, let's say with each epoch, okay, your loss, let's say this is your training loss, right? With each epoch, you're not changing much. You're stuck here. You're not changing at all. One of the reasons could be that this is your local optima. There are two cases here. It could be a local minima, which is perfectly all right, or it could be a saddle point, right? It could be a saddle point. And SGD, simple SGD or mini batch SGD cannot come out of your saddle point very easily, right? So your momentum and Nesterov accelerated gradients work fairly well. They work well in most cases. But they're sometimes slow. If you notice this diagram itself, just notice this. Your momentum is much slower than your ADA deltas and other advanced algorithms, right? So works well in most cases, but slower, typically slower, especially when you have sparse data. When you have sparse data, these types of algorithms are very good. AdaGrad is very good because if you have sparse data or sparse features, right? If you have sparse data or sparse features, AdaGrad works well, but it's better to use ADA delta based approaches because the convergence here is faster, right? Typically, ADAM is one of the most favorite algorithms, and it's also one of the fastest algorithms as far as convergence is concerned. It has all of the best things. So my favorite algorithm always has been ADAM and variations of ADAM that I've not discussed in this. There are some advances to ADAM which people have been publishing over the last few months and last couple of years actually. Okay, but ADAM is one of the most used algorithms in the whole literature. But to introduce you to ADAM, I wanted to walk you through all of these algorithms so that you understand and appreciate the value of ADAM and understand why we came to the concept of ADAM. Because if I did not explain you momentums or AdaGrad or ADA delta, you'll never be able to appreciate ADAM, about its power and about what it can achieve and what problems it avoids. Right? That's why I took a slower path, even though this section is very long. It's worth the read because it gives you a lot of clarity on what some of these great algorithms, because optimization is the problem that you have to solve, right? And optimizers matter a lot. in the real world.